let's dive right into this explainer and unpack the absolutely fascinating, highly engineered science hiding inside a completely mundane snack food. You know, we've all seen them, we've all eaten them, but I bet most of us have completely missed the breathtaking physics, chemistry, and geometry holding every single Pringle together. Today, we're zeroing in on the true secret to this snack's massive success: the highly guarded, mathematically perfected potato paste. Before we step onto the factory floor, though, we really have to ask a foundational question about what you are actually pulling out of that iconic tube. Like, are you even eating a potato chip? Well, the short answer is no. Actually, back in 1975, the FDA mandated that Pringles be rebranded from potato chips to potato crisps, simply because they aren't made from sliced raw potatoes at all. The crucial detail here is that Pringles are only 42% potato. Yeah, just 42%. The rest is a carefully orchestrated blend of alternative flours, starches, and water. So that means we need to uncover the intense chemistry and physics making up the rest of the snack. You see, this isn't just a recipe we're talking about. It's literally a proprietary material designed to solve a very specific problem. Which brings us to Section 1, the broken chip problem, and Frederick Bauer's mission. To understand why this incredibly specific paste even exists in the first place, we got to travel back to the 1950s. Procter & Gamble chemist Frederick Bauer set out to solve a massive structural failure in the snack aisle. Basically, traditional chips shatter in the bag. Customers absolutely hated opening bags just to find greasy, stale potato crumbs and, well, mostly empty air. Think about it. A traditional, flat, or randomly curved potato chip has no preferred axis of stress. When they're packed in a bag together, the contact between chips is point to point. The chip literally doesn't know where to be strong, causing it to just shatter in transit. Bauer realized that fixing this required a totally new, highly engineered material, something that could be molded into a uniform, structural shape for tight, completely air-free stacking. Moving on to Section 2, engineering the potato paste into a proprietary dough. So Bauer's team couldn't just slice raw potatoes. Their irregular cellular structure would simply tear if you tried to mold it. They needed a very specific, highly guarded supporting cast of ingredients to give the paste its exact required stretchiness, or what engineers call the elastic modulus. Of course, you have dehydrated potato flakes milled into a fine powder acting as the base, but the real magic comes from that supporting cast. We're talking wheat starch for structural integrity, rice flour to determine the texture, and cornstarch acting as a really critical binding agent. When water finally hits this precise mixture in the factory's massive mixers, something incredible happens right at the molecular level. The starches activate and the proteins bind together. What emerges initially looks pretty much exactly like wet sand, but it acts like a highly pliable industrial Play-Doh. This paste is the absolute cornerstone of the entire operation. If it's too wet, it won't hold its mathematical shape. But if it's too dry, it just crumbles before it can even be molded. Okay, Section 3, 4 tons of pressure. Let's look at the physical gauntlet. You see, having the right chemistry is really only half the battle. Now the paste must endure an almost aerospace-level physical gauntlet. The sequence requires staggering precision. First, the paste must be strictly maintained between 140 and 160 degrees Fahrenheit. Then, it gets fed through a roller press that exerts 4 tons of pressure per square inch. To put that into perspective, that is enough force to crush a car. This flattens the paste into a continuous sheet just 1 millimeter thick. And get this, laser sensors are constantly monitoring this thickness, because if it varies by even 0.1 millimeters, the dough will cook unevenly and the final product is completely ruined. No pressure, right? After these paper-thin sheets of paste are rolled out, a rotary cutter slices them into perfect flat ovals. The factory workers actually have a playful name for these blanks. They call them doilies or dovals. And in a truly beautiful display of manufacturing efficiency, 99.7% of the leftover scrap dough from around those cutouts is recycled right back into the mixer to prevent any waste. Now, for Section 4, the hyperbolic paraboloid. Let's talk about the geometry of snacks. To actually solve the broken chip problem, we've got to explicitly connect this chemistry to geometry. The shape itself is called a hyperbolic paraboloid. I know it sounds like an intimidating mathematical term, but it's really just the technical name for a saddle shape. It features what's called negative Gaussian curvature. That just means it curves up in one direction and down in the perpendicular direction simultaneously. And this isn't just for looks, guys. It is the exact same load-bearing geometry used by architects for those massive, sweeping stadium roofs like the London Velodrome or the Scotiabank Saddle Dome. The core structural benefits here are wild. Because the opposing curvatures brace each other, force is distributed evenly across the entire surface rather than concentrating at a single weak point. This is exactly why a bottom Pringle doesn't shatter under the weight of a full stack in the can. But remember, this complex geometry is only achievable because of the paste's precise elastic modulus. The dough ovals are sandwiched between two molds to force them into that saddle curve, and then they're fried in 392-degree oil for exactly 11 seconds. Bam! The starch structure sets instantly, locking that hyperbolic paraboloid in place forever, without the dough tearing or snapping back into its flat shape. And finally, Section 5, the anatomy of a snap, a geometrically efficient fracture. All of this engineering builds to the absolute most satisfying payoff of the entire process, the moment you take a bite. Because the saddle geometry is entirely under uniform tension and compression, it just doesn't allow the dough to flex locally when you bite into it. Instead, the stress builds up uniformly across the entire chip until it hits a critical threshold. When it finally gives way, it shatters everywhere all at once. So that loud, extra crispy snap you hear is literally the acoustic signature of a geometrically efficient fracture. How cool is that? And you better believe they fiercely protect this engineering standard. To ensure this structural snap and flavor profile are absolutely flawless, professional taste testers actually perform over 7 million quality checks a year. They take randomly selected chips and chew them exactly 15 times inside special red-lit rooms. Why red lights? Well, it completely eliminates visual bias, forcing the testers to focus entirely on the texture, snap, and flavor of the paste. If even one chip fails this test, thousands of canisters from that batch are immediately rejected. No exceptions. So, I'll leave you with this thought to ponder. We've seen the chemistry of the flour blend, we've talked about the 4 tons of rolling pressure, and we've explored the negative Gaussian curvature of the molding process. The very next time you pop open a can and reach for this incredibly engineered, self-stacking, hyperbolic paraboloid, ask yourself, are you just having a snack, or are you biting into a true marvel of mathematics and food science? Thanks for joining me on this explainer, and keep questioning the extraordinary hidden inside the ordinary.